All right, friends and neighbors, welcome back for another CCNA networking video. This is another one of those big chapters, plus it has things that are put together in the chapter that don't sort of go together. So I split this one into two parts. So today we're going to do Chapter 12, Miscellaneous IP Services, Part 1, and we're going to do the First Hop Redundancy Protocol, and we're going to talk a little bit about SNMP, the Simple Network Management Protocol. So in this video, we got our key topics. We're going to do part of those again. The exam section is IP connectivity, First Hop Redundancy Protocol. We'll see that that's a category. And then infrastructure services, and we're going to stop short after SNMP. We're not going to do FTP and TFTP today or the Cisco iOS structure. And then we'll finish with the Do I Know This Already questions. So our key topics today are going to be the common characteristics of first hop routing protocol. So we'll talk about what, sort of they all have in common. We'll chat just a little bit about HSRP, VRRP, and GLBP. We'll do the concepts and failover results of HSRP. And that I'm actually going to do a little bit of a demo for you on that one. And then we'll talk a little bit about SNMP and how it communicates with network devices. And then we'll talk a little bit about how network devices might communicate with a network management server, or the NMS. And then we'll talk a little bit about the configuration and options with SNMP, the Simple Network Management Protocol. And I'll also tackle one of the tougher spots here, which is the OIDs. Okay, First Hop Redundancy Protocol, FHRP. Now again, what I'll say at the outset here is that this is a category. And the whole idea is that if you've got multiple connections off of your site, wouldn't it be great if there was a way for that connection to fail over to keep your routing connectivity up and running? Now, we build redundancy in of all kinds, so right down to the host. So I could have this host that I'm sitting on could have 2 Ethernet NICs, for example, or 2 wireless connection, or wireless and wired. So that would be redundancy. We do that with servers all the time. So we do NIC teaming between interfaces on a server, and sometimes that's for redundancy, and sometimes that's for sheer capacity. We can add extra links anywhere between switches, between routers. And of course, we could add extra devices too. We could say, I'm going to put in another switch and have more than one connection between my routers or between segments of my network. So we do redundancy all the time. Now, redundancy doesn't have to be just for your network devices. You can also think about, well, where is my power coming from? What building am I actually housing things in? So we can do redundant power supplies, redundant power grids, redundant locations. So there's all kinds of redundancy that we build in. And this is part of our sort of general discussion about our infrastructure. Now, just because you put in an extra link or an extra device doesn't necessarily mean that failover is going to work. Sometimes you need a protocol to get that to work. So, for example, we have routing protocols that handle that. Routing protocols are fabulous because not only do they take the manual configuration out of things, but they are designed to handle a whole bunch of problems, like you added a router, you subtracted a router, you added a route. So there's all kinds of things that routing protocols automatically figure out for us. And if you didn't have a routing protocol, it doesn't matter how many extra routers you put in there, it wouldn't work. The same thing happens at layer 2. You can put extra switches in there and connect them all in a loop of some kind for redundancy. But if you didn't have rapid spanning tree or even 802.1d early version spanning tree, the failover wouldn't work because there'd be no way to automatically recover the ports. Now, those are sort of protocols and ideas that we use all over the place, and they do multiple jobs, right? A routing protocol has multiple jobs. But some protocols, like FHRP, are really sort of designed just for redundancy. And so there's a difference between, do I use a routing protocol or do I use a redundancy protocol of some kind? So things always break. What you can absolutely count on in your network topology is that stuff is going to break. So redundancy, failover, and uptime are all about designing a network that can survive these outages, these failures, these breaking points. One of the key ideas in your network design is that you want to avoid what we call single points of failure. If you're looking at your network topology and you go, if I take away that right there, or that breaks, is there no other way for traffic to flow? And this is not much different than any other system, right? If I have one electrical connection to my house and that electrical connection goes away, well, I'm dead in the water. So I might get a generator, right? So that would solve that single point of failure. Now, statistically, at least according to the chapter, WAN links are the most likely to fail for a variety of reasons. It might be capacity, it might be equipment, it might be backhoe failures, but those are the most likely to fail. So we want to put in something in place that handles redundancy and failover at that location. And it's not just a matter of hooking up another router. Now, one of the downfalls about all this extra redundancy and failover capability is that it can be expensive. WAN links are expensive, devices are expensive, man hours to do all this and monitor all this, these are all expensive, but sometimes they're absolutely necessary. So why is a first hop routing or first hop redundancy protocol so important? Why is it necessary instead of just, depending on your routing protocols? Well, let's think about this example above me here. Take a look at PC0 and PC1. In the case of this topology, where would we point our default gateway? Would I point to router 2? Maybe I point to router 3. And we know now that hosts really, they get their gateway from DHCP, so they're going to point at one of them. Let's assume that they're pointing at router 2, this interface on router 2. And then router 2 goes away. Somebody unplugged it. Maybe the connection died on one side or the other of both. Maybe this connection on the switch died. So the point is that you can't get to that router anymore. So they have no way off of the network. Can they automatically fail over to a new default gateway? The answer is almost always no. They can't figure that out. Now what we could do also is we could say, well, wait a minute, we'll send PC0 to router 2 for a default gateway and PC1 to router 3 for a default gateway. And that seems like a reasonable solution. And then when one of the routers goes away, you've only lost connectivity for half of your nodes. Okay, so that is a real problem. So these are sort of the issues, right? DHCP assigns the gateway, but the nodes would have to learn another. They don't have a really good way of doing that, especially since we no longer really do router solicitation or router advertisement, unless you're IPv6. If you manually configured these and you didn't rely on DHCP, then you would have to go in and touch all of the nodes. And users are usually not good at this kind of thing. So this is a real problem. A much better solution might be that if these two routers shared something called a virtual IP address. So it doesn't exist in actual physical location, but it's a virtual IP address that they both share, and that the hosts point their default gateways at that virtual IP address. And then we get the routers to talk to each other and let them know, or let each other know what their status is. And that way, if one of them has a problem or one of them times out, then we know to fail over and use the other router. So that is the idea behind all first hop redundancy protocols. We're going to create a virtual IP address. We are going to have the nodes use that as the default gateway, and the routers are going to talk to each other to determine if they're both still up and running. So for the exam, the only one that you really need to know about is the hot standby routing protocol. But I would be remiss if I didn't say, well, look, there are other routing protocols out there that handle some level of redundancy or load balancing. So there's the sort of industry standard virtual router redundancy protocol, VRRP. You can find that in RFC 5798. There's the gateway load balancing protocol, hint, hint, wink, wink. That's not the same as HSRP, and we'll talk about that here in a second. Now, again, I'll refer you to this diagram over my head. It's part of the other diagram, and all that I'm showing you here is that now these two hosts are now pointing at this virtual IP address virtual MAC, and that one of the routers, and only one of the routers, is active at a particular time. Okay, so HSRP concepts. Multiple routers act in either active or passive, active or standby sometimes, and only one is active. So the other router is not doing anything, which is another reason why redundancy protocols can be a little expensive, because you got a router sitting there not doing anything. They share, all the routers involved, whether it's 2, 3, 4, whatever, share this virtual IP address and virtual MAC address. And so the hosts all point to that virtual IP address and virtual MAC address. Whatever router is active, that's the one that's going to do all the forwarding. The routers also send HSRP messages between themselves to give an indication of not only am I configured and what my priority is, but that I'm alive and well. And this is really, really important. When one of these fails, so let's say router 2 fails, the hosts still believe that they're going to use this virtual IP address as their default gateway. So they don't have to do anything. In fact, because the routers also share a virtual MAC address, the hosts don't have to do anything with their ARP tables. That becomes really, really important. Now, there is one bugaboo in all of this, is that the switch source address tables learn where the active router is in terms of its MAC address. And so the MAC address will still be part of the switch source address table. And so there are differences into how we configure HSRP to avoid that particular problem, but we have to be aware of that. Now, another key idea here is that redundancy is not load balancing. Remember that only one of the routers is active at a particular time. The other one is just sitting there in passive or standby mode. In fact, standby is the keyword and tricky phrase that we want to remember here. But what we could do is that we can say for a particular VLAN or subnet, one router is active for that subnet and the other router is active for that subnet or VLAN. And in that way, some of the hosts send traffic one way and other hosts send traffic the other way. And so in that way, you're sort of splitting the traffic between the two routers, and the routers are still there and available in standby for the network that they're not serving or the VLAN that they're not serving, but they are actively handling another subnet or VLAN. Now, the key to that, of course, is that they would have to be VLAN or subnet aware, and so they would have to know that they could get to all of the VLANs or all of the subnets depending on your configuration. The book example for this is that we've got router on a stick, and for router on a stick configurations, if you remember, we've got we're trunking up to the router, or we have a lot of sub interfaces on the router. Trunking is a very common thing, so this becomes 802.1q out here and out here, and so the routers are fully aware of all the VLANs and subnets. All right, let's do a quick demo. So here is a small router configuration. I've already built the HSRP, but we'll put it all together here. But let me explain what we got going on. We have the 192.168.1.0 network out here. We have the 172.16 network, and way over here we have the 10 net. Now this looks like it should be two separate lines, but remember, this is where our redundancy is going to be configured. So the two routers, router 2 and 3, are talking to each other via HSRP, and they're sharing this virtual IP address. So their physical addresses are 192.168.1.253 and 1.254, but the virtual address is 99. So let's take a look at our host configuration. We can see that the default gateway that it's pointing to is 1.199 or 1.99. And we're going to try and communicate with 10.1 over here. So we're going to look at traffic going from 192.168.1.1 to 10.001. So we take a look at that. We'll see if this works, and that works. Now a good question is, what direction is it going into? Whoops, we got a timeout. There we go. Our table's updating. Okay, what direction is it flowing? So let's take a look at our simulation, and we're going to do the exact same thing, but we're just trying to understand how the traffic flows. So there we go. So the traffic is going out through the top router. We'll send that out a couple of ways, and it's coming back. And again, now there is that purple message right there, or this dark one. is the HSRP messages between the routers. But again, I'll do the config for you. Just for fun, you saw that it went down to the host. That's because it's a multicast traffic. So the routers are communicating. And then there goes our ICMP again. The switch is trying to figure out what the deal is with the MAC addresses. There we go. But this bottom router is not active. So we go to real time. Now, full disclosure, I do have a top secret route here. If you remember when we were doing our static routes, I've installed a floating route on this router so that when one router fails, the other one picks up. So this right here is a static route that's not being used right now. And I'm using this static route to get back to the 192.168.1.0 network. So that's just, how this router 0 figures out that it can still get back when this router dies. So let's take a look at our configuration. We'll do a show run first, and then we'll go through the commands. So an HSRP config is actually pretty straightforward. I'm going to tell it, there's my IP address, but I'm going to tell it what my standby IP address is. I'm going to give it a priority, higher is better, and then we're going to pay attention to a particular interface for when that interface goes down. And that's pretty much it. We can see that we've got, the other IP address, and then I've got a static route out there. And that is it. On the other router, we have a similar configuration. We can see that it thinks it's in standby right now. And here is its configuration. So the same virtual IP address, a little bit lower priority, and then it is also keeping track of the WAN link. Now I'm going to do the commands just for fun, just to make sure that we get them in here a couple times. So what would I do? I would say config T, and because the gateway here is the side that I'm interested in, right? The side that is going to be my gateway for my hosts, I'm going to go to that interface, and I'm going to say standby. Now, if we take a look at our question mark here, we've got these things to worry about. Now, we're going to do some of these options. We're going to ignore others. So we have a group number. Well, that is the group of routers that are actually talking with each other. So I'm going to do group 1. And after you do the group number, what are you going to do? Well, we need to do an IP address, and our virtual IP address is 1.99. And that's it. You don't need to do a mask or anything else because the physical interface already has a mask. All right. Notice also that we established layer 2 connectivity. So these two have to be able to ping each other. If you put them on different networks, this is going to be a problem. So let's do a couple of other things with our standby group 1. What else do we need? This is where I did the priority. Right. So we're going to do priority 10 again. Now, if I change the priority here, then that would cause the other router to start trying to figure out who's in charge. And that's what this is right here. Preempt, overthrow lower priority active routers. So that is to say, if you come back, right, and you've got an active router that has a lower priority, you would say, well, wait a minute, I'm back now. I want to be the guy again. But maybe you don't want to do this because that would be, while you switched over, there'd be a delay in connectivity for the host. So that's a configuration option that you have. And the thing that we're going to track is going to be one of our interfaces. Now we're worried about the WAN side, so I'm going to say G0/0/1. There we go. Okay, and that was pretty much it for this base configuration. All right, now we know that the traffic is flowing out across the top router. There it goes. And when it comes back, it goes back across the top router again. We also know that the routers are communicating via HSRP. So I'm going to step through a little bit. We've got our HSRP back. Now let's take a quick look at HSRP. A couple of fun things here. We can see that the destination is a multicast. So 224.0.0.2 is an all routers multicast. We've got a particular port number. And then we've got some timers associated with it. We've got our group, our priority for this particular message, right? So details about HSRP. There's the physical interface for this router, and here is the virtual IP address for this particular router. So you can see there's, a nice chunk of information going on between the routers. Now what I'm going to do is I'm going to shut down my outside interface. So I'm going to say shut. So this is now down, and so the router here is going to want to fail over and say, hey, listen, I'm watching this interface. My HSRP configuration says that I have a problem now. And we can see that this has been reflected, right, with my neighboring router. Now, what we can also do is take a look at our show commands. If we go all the way down here, we can see that there's some standby commands right there. So what we're going to do is we're going to say, tell me a little bit about our standby configuration. We can see that we're in group 1 right here, the virtual IP address. There's the virtual MAC address that they're sharing, some timers associated with this, my priority, and the group, right? So this is all my configuration that I have right now. Now to speed things up a little bit, because I do have this switch and the source address table will be a little bit of a pain, I'm also going to kill off the inside interface. Now remember that the hosts have no idea that this is happening, right? So the host believes that it was going out through this upper router. I'm not going to touch the host at all. And so the real question here is, can these routers figure this out between them? So let's take a look at our transmission. We'll do the simulation again. And now we're going out through the bottom router. So this means that my bottom router picked up the load. My bottom router realized that it now had to be the default gateway, it had to forward things. And also, we have to realize that this router is responding to its virtual IP address and MAC. And so it's handling, not only is it waking up to actually start forwarding traffic, but it's also was part of the configuration for my hosts. Well, there we go. There's a very small, simple HSRP configuration. All right, a complete segue away from routing is the simple network management protocol. So we got some low-numbered RFCs to get us started here. Very early on in the internet's life, right, we can see RFC 1065. They were sort of going, well, all of these devices, hosts, routers, switches, bridges, they all share some similar ideas. They all have tables, they all have interfaces, they all have statistics. Wouldn't it be great if we could call them variables? And wouldn't it be great if we could actually reference those variables and then ask devices how they're doing? So that discussion was the genesis of 1065, the structure and identification of management information for TCP/IP-based internets. So just a quick blurb from the RFC, right? This memo provides the common definitions for the structure and identification of management information for TCP/IP-based internets. So think of that as variables or objects on the devices. So the idea is that stuff on the devices ought to be able to be organized and then maybe queried. Now, how is this all put together? How is it all structured? Well, we have the structure of management information, which is RFC 1065, which describes how all this is put together. And I'll show you a couple of examples here in a minute. And then comes the protocol. So RFC 1157 is the simple network management protocol. Implicit in the SNMP architectural model is a collection of network management stations and network elements. So you got all the things that are in your network. Network management stations execute management applications which monitor and control network elements. So that is this. If you look above me here, that's the SNMP manager. So the SNMP manager is going to be sort of in control, and then we've got all of our devices. And all of the devices are running what's called an SNMP agent. And the network management system, the manager, can query all of these devices via the SNMP agent resident on them. All you got to do is turn it on. Now this is SNMP v1, which is still out there today, but probably the most popular versions in enterprise anyway is SNMP v2c, which is a return to some of the earlier ideas, in particular the community string. and then SNMP v3, which adds some security. I'll touch on those later on. So we have all these variables, and then we have a way to organize them, and then SNMP itself is the protocol, the very structured protocol that communicates between the manager and the agent on the devices. So the queries have a very particular format. We've talked about the variables, and we talked about the, sort of the objects, and that they're organized. Well, what are they organized into? There's a database. So the Management Information Base, or MIB, is what every device has on it. So your PCs have it, switches have it, routers have it, and it's the collection of all the things that might be variables, tables, statistics, interfaces, etc., that you might want to ask about or might want to know about. Now, the MIBs are going to be different between devices. So a switch is not a router, and a router is not an access point, and so on. So each one of these has its own tailored MIB. And vendors add their own stuff based on their own feature sets. So the MIB is the database that has all of these things that can be queried. And all of those things that can be queried have a very particular format. Now, how does the querying work? Well, the network management system, or the manager, can say, hey, tell me about this. And when it does that, it says, all right, I'm going to ask you for this thing, and I want you to give me that information. And the message that it uses is called a GET. Now, there are a couple of flavors of GET. There's a GET, GET Next, GET Bulk, and it depends on which version of SNMP you have. But if you imagine, if you say, tell me the status of interface G00, well, that's sort of one thing. But if you say, give me the status of all of your interfaces, well, that's a different kind of query. If you tell me, give me the statistics for all of your interfaces, give me your routing table, right? These are different kinds of operations, and it might require multiple messages to do that. Now, a device can also be told, listen, when you see this event happen, I want you to tell me about it. So event notifications come from the agent to the network manager, and those are called traps and inform messages. So a trap is sort of fire and forget. This thing happened. This thing happened. And it just hopes that it gets there. Now the inform, we call that a more reliable version because it's acknowledged. So an agent says, hey, I got to tell you about this thing. You're supposed to acknowledge that you got it. And if you don't acknowledge it, I'm going to keep sending it to you. Now that is all querying stuff, right? Tell me about what you got going on, or I had this thing going on. SNMP also has the ability to configure a device over the network. Now, obviously, danger, 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 because if anybody learns your community strings or anybody learns your security, then, or if you don't have any of those going on, right, then anyone can configure your devices depending on what you've allowed. So most organizations that I've talked to or that I've worked with, they don't have SNMP set operations in place at all. We don't want to do that across the network. So here is an example of the MIB structure. So we think of this in terms of a tree or like a tree. And the idea is that you work from the root of the tree down to whatever object you are worried about. Each object, each variable, each interface or table or statistic has an object ID. And you reference that object ID by going down through the tree and getting all the numbers. So if I wanted to talk to this thing about UDP, I would ask about 1.3.6.1.2.1.7. And that would be the object ID that I would specifically query. So the MIB is very hierarchical and organized from top down. So it's this sequence of numbers. Let me show you an example. So here is an SNMP packet. I caught it yesterday for this video. And we can see a couple of things here. We've got the SNMP port number that we're using. We can see that there's a public string. So this is, those websites that give you the default IP address and login for all the devices that are out there, right? They also provide community strings for the SNMP messages. So the community string idea here is that if you have devices that are going to do SNMP, you set up your manager and your agents with a community string so they know that they're supposed to be talking to each other. Now this is clearly clear text. So it's clear text, right? You can see it. So anybody capturing your SNMP messaging could see what your community string is. We can also see that this is a GET request. So this is asking for information. And what information is it asking for? Well, there they are. Really hard for humans to read this, but we now know that this is an OID asking for something very, very specific. And we can see that they all start off all the same, but then this is 3.2.1.5.1, 3.5, and so on, 3.5.1.2.1. So these are different objects. This happens to be communication with a printer. So this might be asking about paper levels, ink levels, things of that sort. Now, like many management protocols, link layer discovery protocols, Cisco discovery protocol, SNMP, they can be very insecure because they're willing to communicate an awful lot of information, and it's all clear text. To start off with, we have this idea of a community string. So if you were an interloper and you didn't know the community string, then you could not find out the information. The agent would not respond to you. Now there's two flavors of configuration for strings, right? One is read only, and this allows the get. Read write allows the get and set, and these are the things that we don't usually allow. But we know that these are clear text, and so if anybody caught them in the network, they would be able to get access to your devices or at least query those devices and find out what's going on. Now, SNMP v2c was a return to the community string. So version 2 got rid of the community string and then everybody wanted it back again. So version 2c, or v2c, was a return to the community string. SNMP v3 adds additional features for more security. So message integrity. So we see lots of message integrity checks. We see that in wireless. We see that with MD5s. We see this checksums. And it's just a calculation that says, hey, here's a calculation on the data. If your calculation is different than mine, right, then something happened to this message along the way. We can do optional authentication and encryption of SNMP. Most folks opt not to do these, but if you have a secure environment, DoD, government, something of that sort, private contractor, you might want to consider encrypting and authenticating your SNMP traffic. And then lastly, agents know who they're supposed to be talking to. So it would be really awesome if you set up ACLs that said the only queries should come from the network management system. So you could set up an extended ACL that says the only thing that I'm allowing through here are SNMP queries from my network manager instead of somebody else. All right, do you know this already? Question number 1, router 1 and router 2 attach to the same Ethernet VLAN with a subnet of 10.1.19/25 with addresses 19.1 and 19.2 respectively, configured with the IP address interface subcommand. All right, so we got two routers, both on the same VLAN. Host A refers to 19.1 as its default router, and host B refers to 19.2 as its default routers. Routers do not use any First Hop Redundancy Protocol. Which of the following is a problem for this LAN? And the answer there was D. If one of the routers fails, then that host cannot get off of the network, whatever host was using that for a default gateway. Question number 2, router 1 and router 2, same configuration, but this time we've got the First Hop Redundancy Protocol configured and host A and B attached to the same LAN, and they have the proper configuration, so they're using the virtual IP address. Which of the following statements is true? I had a cut and paste error there for a sec, but here we go. If upon failure, the hosts will use the remaining router as their default route. Question number 3, router 1 and router 2 attach the same VLAN. There we go again. And the routers use HSRP. The network engineer prefers to have router 1 to be the default router when both router 1 and 2 are up. Which of the following is likely the default router setting for the hosts in this subnet? They're going to use another different IP address. They're going to use that virtual IP address. They will not use 19.1 and 19.2. Okay, so the other questions are about SNMP, TFTP, and FTP. We'll hit those next time. So the Chapter 12, Part 2, look ahead. We're going to be looking at the Cisco iOS file structure because we want to figure out how to update and change the iOS image. We're going to look at file transfer protocol and trivial file transfer protocol. What can we do? How do those work? And how do they fit into the Cisco iOS operations? So we'll do protocol basics and operation for both of those. And then we'll finish off with operations to update and verify Cisco images. So that'll be fun. We'll look at the actual structure that you see on your routers and switches. All right, well, huzzah. This has been router redundancy and SNMP. We now know that the First Hop Redundancy Protocol is actually a category that includes things like HSRP, VRRP, and GLBP. But they all share the same sort of characteristics, right? They are going to have a virtual IP address between them. The hosts are going to point to the virtual IP address as their default gateway, and the routers communicate using whatever redundancy protocol you're going to see. In this case, in our demo, we used HSRP, and that's the one on the exam. We also talked a little bit about simple network management protocol. We know now that there's structured management information. We know that those are organized in a tree that we reference via OIDs. We know that SNMP is the protocol that queries or pulls, traps, or informs those OIDs or uses those to transport the OID information. There we go. Good stuff. Good stuff in this video. Like and subscribe for the Cisco iOS file structure, FTP, and TFTP next time. And no matter how you're doing your redundancy, may those packets always reach their destinations. And hey, this is CCNA. We're doing router redundancy. No matter how challenging this gets, you can do this.